Hi, friends. Now we will see the next topic, slot antenna and microstrip patch antenna. Okay. Sorry, here's the spelling mistake. Microstrip patch antenna. Okay. Now, now we just see what is slot antenna. So, name itself is defining like slot, right? So, what is a slot? So, here in the picture, we can see we have an conducting sheet. So, we have a conducting sheet here. So, right in the conducting sheet, we are just going to make a slot or a hole. We are going to make, and then to that particular slot, to the ends of the slot, we just connect uh, two wires to that is transmission line. We just connect, and this will be like a slot. And now this particular slot is made to work as an antenna, right? So how we define slot antenna as slot antenna is a type of antenna with an opening cut of a certain dimensions in a metallic conductor, which is excited using a two-wire transmission line or coaxial cable. Okay. Now we can see what's its frequency ranging. So its frequency ranging is from 300 megahertz to 30 gigahertz, right? And then the surface of the conductive plate, then on energizing the slot, the electromagnetic wave is radiated, thus acts as an antenna, right? Due to the presence of a slot, it is named as a slot antenna. So this is about the slot antenna, right? So we are going to energize the conducting plate, and the radiation will be emitting out from the plate. Okay, so that is like slot antenna. Right. Next, now this slide has been taken from NPTEL. Now we can see this the relationship between the complementary impedance and the slot impedance. Now we can see here, that is whatever the slot which has been taken, right? That is the slot in the conducting plane, and the complementary dipole, that means whatever the portion of the uh, conductor which has been removed, right, that will be taken as a complementary dipole. So the impedances of these two, so the impedance of the slot and the impedance of the complementary dipole, if we do the product, the product is a constant, that is as eta square by 4. So we know what is eta. Eta is nothing but the intrinsic impedance. So eta square is 125 the whole square, or 377 the whole square by 4. So that is a constant being maintained in the slot antenna. Now we can see this, the slot antenna and then complementary dipole antenna. So what has been taken here is the length, right? So what should be the distance of the slot? So it also depends upon the wavelength. It is better to have the slot of the length lambda by 2, and similarly with that particular slot we get a complementary dipole antenna of the same length of lambda by 2. Right? Now, as we were discussing that the intrinsic impedance is about 377 ohm, exactly it is 376.7, right? So if you can see the slot, and that is the impedance of the slot antenna is like Zs is equal to 35,476 by Zd or Zc, whatever we have taken as complementary impedance, right? Complementary dipole impedance, right? So in general, the impedance of dipole can be written as Z suffix d as Rd plus Jxd, right? Where Rd is the complement, that is the resistance. R is capital R is the resistance, and capital X is the reactance part. And now, if we just see the value, we can just divide in terms of the real part and the imaginary part, right? So now here, for a dipole, so if we can just go for a dipole, right, and half-wave dipole antenna, so that we know that the half-wave dipole antenna will having about 73 ohms, and with a phase shift it may be like 0.42. So yeah, approximately zero point 0.6 we get, 73.6 we get. The impedance of the half wave dipole is 73 plus j 42 ohms, right? And right, and similarly we can see here others B, right, the half wave slot antenna. If you can see the half wave slot antenna, by substituting, that means that slot whatever we have taken that in terms of RD plus JXD in that form, if we can just substitute, we get the half wave slot antenna, and that ZS is equal to 363 minus J21 we get, right? And similarly the next one we can see the reduced half wave dipole. If the value is less than 0.5 lambda, so this is the equation we have, that is dipole impedance as 70 plus J0 exactly, and the ZS will be like 530 ohm, that is for the reduced half wave length slot antenna. And the next one we can see that is full wavelength dipole. So the full wavelength dipole is approximately 0.925 lambda. Then the impedance of the dipole is about 710 plus J0, and the slot of the particular dipole, that is ZS, that will be like 50 ohms. Now this is the full wavelength slot antenna, which is about 50 ohms. This is being used the figure F, which is as full wavelength slot antenna, which is getting like 50 ohms, that is used in practical cases, right? Next, and this slide similarly we have taken from NPTEL. Now the slot antenna, the far field equations, just remember that far field of electric and the magnetic field, right? So we can see that the radiation pattern of the slot is identical in shape to that of the dipole, except that the E and H fields are interchanged. So only for a dipole we are having in terms of E theta and H phi, but here it is like E phi and H theta. That's the only difference, and it will be nearly the same. So this is the radiation pattern of the slot antenna, depending upon the directions, if you can see, right, towards your xy plane. So it has a bounded charge of oscillator, right, and fine. So this is the radiation pattern, right? Then now the next video we will go on to the microstrip patch antenna, and thank you for listening to this video. Have a great day ahead. Thank you so much.